Hey everyone, good afternoon and thank you for joining. Currently, I'm a data scientist working with PayPal. I have overall experience of around 4 years and I have worked in various, let's call them industries or segments. My experience revolves around building end-to-end ETL pipelines to working on strategical data analysis. And I'll try to help everyone out here with what exactly you need to think about or even take care about before you import any model of your choice or any library. So we'll try to progress it in that way. Let me share my screen so that I can show you. In fact, okay, screen share. So we'll start with a basic introduction about data science. I'm sure everyone here knows what data science is in basis or what exactly the term means. But just to give you a brief recap or walkthrough, data science is a field which deals with two domains or two subdomains, as the name suggests, data and science. So the thing about data science is it brings in the decisiveness of data with the flexibility of science, right? These days, data science has been a term that has been thrown around very loosely around the industry. And thanks to the title sexiest job of 21st century by Harvard, I think everyone and anyone wants to be a data scientist, and industries are throwing this term around loosely. What is happening is they are, yeah, hi, the screen is not visible. I'm not sharing the screen, some issue on that end. I'm sorry. So a lot of tasks and a lot of segments have been clubbed under this single domain of data science. If you look closely under this umbrella, you'll see that people are working on data analysis using SQL, Python, R, and they are data scientists. You'll find that people are working on data visualizations using various tools. It could be Python, R, Tableau, Power BI. They are data scientists as well. Then we've got the favorite term of everyone, machine learning. So people working on forecasting and machine learning, deep learning models, and they are called data scientists as well. So my point is this particular term is being vaguely thrown around and a lot of things are being clubbed under this single domain. But one should always know what kind of path or career they want to proceed or pursue, and they should make this choice of coming into data science with clear mindset. So when you walk into data science, you should know if you want to work on statistical data analysis or if you want data visualizations, or again, the favorite of everyone these days, machine learning models. So you should have that clarity before joining in any job of your data science career. But this session is not getting in depth about what you need to do once you are there or once you're making that choice. The session revolves around what kind of steps you need to take or think if you're working on a data. So I assume everyone might here know that data is the new oil of the century. Earlier, oil was the most heaviest or valuable item, but now it's data. So even though data is quite, let's say, valuable, it's not in the form that we want. We have to do a lot of things. We have to work on clearing it. We have to work on blending it, and a lot of problems that we have to solve before we can use any machine learning model on it. So just to give you a brief walkthrough of some of the steps that you might need, I was talking about what exactly do you need to do or think about before you pick any of those fancy models that you might heard of, random forest, XGBoost, deep learning, or whatever. So you need to think about a lot of things ranging from whether or not the data is in the form that you require. The data can have missing values or null values. And that could be a problem for a few of the models. There are some models available that can tackle that, but mostly you'll have to deal with these null values. You'll have to do something about that. The next step is, does the data have outliers or not? And what are outliers? We'll talk about that in a brief in about 10-15 minutes later when we are on that topic. And lastly, is there a need for feature engineering or not? So I have done missing values treatment. I've checked the outliers. Do I need to go for feature engineering? What exactly it is and why do I need it even if I do? So we'll talk about these three sections in a bit of depth for now. And let's see how far it goes. So talking about the first step, that is imputation, right? So, and again, if anyone has any question, you can post in the Q&A section and I'll be happy to take them after the presentation is over. It will help not to break the flow for everyone. So yeah, talking about imputation. Imputation is the process by which you handle or fill in your missing values. So let's say you pull in your data from any source. It could be any apart from Kaggle. Kaggle is a pretty amazing website, but the data is already clean up to a large extent. So when you're working on real life data, you'll have many issues with it, and missing values would be one. How do you tackle that missing values? How do you tackle those missing values? You can do a lot of things. You can work on extrapolation. Now, extrapolation is completely different term. We won't discuss much about that here, but a brief introduction about that. Extrapolation is the process by which you use your current data to extrapolate or to forecast what exactly your data might look like, your dependent variable, the independent variables. But imputation is something which you will use when you have got, let's say you've got 10,000 rows of data and 300 of them are missing or 25 of them are missing. They are missing in between. So you'll use imputation to fill in those missing values. Now, what exactly will you do in imputation? You can use various formats, like you can use mean, you can use median, mode or most frequent, and then there are constant values as well. So I'll explain each of them in a bit of depth. When you use mean, what you'll do is you'll take all the data that you have, and by all the data, I'm talking about training data. It's better if you split your data into train and test segment before doing all of this experiences, because else it might lead to data leakage and some other issues. So you've got your data handle, you've split it in train and test segment. Now you're looking at your train data and it has got some missing values. Let's say you're looking at age column, right? So age column could have values from 0 to 50, 60. 0 won't be a value. So let's say that it's a data about the working class people of India. So the values would range from 18 till 55 somewhat. You have 10,000 rows of data and around 50 of them are missing. You have to deal with those missing values, right? The most simplest option that you can think is you can drop those rows. If you have millions of rows of data and 50, 60 values are missing, you can drop them. It won't create much of a hassle because you still have enough data for your model to train on. But in other scenario, when you cannot drop those rows, when you have to do something, you can either go for mean. Now, mean, as the name suggests, all you will do is you'll simply take the average of all the available values in each column, and you'll use that average value to fill in those missing rows. Why can't you use mean, or why should you use mean? Mean is highly sensitive to outliers, right? Outliers, as I said, will come in the next section, but just bear with me for now. What will happen is, let's say that your age values, they range from 18 till 55. You take the mean value comes around 35 or 36, depending upon your distribution. You're good to go. You can fill in those 36, you can fill in that 36 value in those missing cells, and your data looks amazing. But what if your data contains outliers? Let's say due to some issue, some human error, or you took the data via online form or something, and few people, they made some mistakes, or it could be any issues, and the age got entered to 1,000. So now you have 10,000 rows of data. Hi, I guess Pawan, if it's not an issue, can you post your question in Q&A? We'll take it right after this session if it's not so urgent. So let's say you have got 10,000 rows of data and around 500 rows of them are 1,000 value. So you can imagine how drastically it will affect your mean. So using the mean value, you won't be tackling those missing values correctly. The missing value or the mean value you fill in won't be theoretically or statistically correct, because it will be highly affected by those 1,000 value, 500 value points that you had. That's why you shouldn't use mean. Median, I am sure everyone here knows what's median, but just a quick recap over median. If you take your data, if you distribute on a single line, median would be the exact center point for your data distribution. The formula for even and odds are different, n by 2 and n by 2 plus 1, depending on what you have. So median is actually a better choice than mean, because median is not affected by outliers. No matter what your values are, let's say if the same example, you've got 10,000 rows of data. Out of them, 100 rows of data are 1,000 value. Another 100 rows are 10,000. And then you've got around 300 rows saying that the age is 20,000. You distribute your data on a straight line, you find out the mean, which will be the center point. It is not affected by those values, right? It will still say that, okay, out of 10,000, the median value lies somewhere around 5,000, 5,001, the middle point of that. No matter what you have on those values, it won't be affected by that. So median is actually a better way to impute those values as compared to mean. What will you do if you're tackling with categorical data? So categorical data is string-based data, or something that you cannot calculate on mathematical operations. So if you've got, let's say, email addresses or names, you cannot calculate the mean and median of those columns, right? In my point of view, it's even useless to use names and email addresses in the data because they won't give you enough information. But let's say that you are using, you have a column called gender. So gender could have values and you want to treat the missing values. Now you cannot calculate mean or median of gender. That's not possible, right? So what you can do is you can take out the most frequent or the mode. Now, I'm sure mode and most frequent are pretty simple in themselves, but it's the value that occurs most in the given data. So you've got data distribution for gender, male and female values, 10,000 rows, 3,000 are male, and let's say 6,500 are female. 500 are missing values. So you find out the most frequent or mode, it comes out as female. So use female gender to fill in those missing values. It is still better than using mean because mean is still prone to outliers. A problem with this approach, with this mode approach again, is let's say that you've got two columns. You're working on any e-commerce platform you like. It could be Amazon, Snapdeal, Flipkart, any e-commerce of your choice, any e-commerce platform, you're working on that. You've got two columns. Column number one is the order date, and column number two is the shipment date, right? So your column one tells that, hey, on 13th of August 2019, a particular customer made an order. And column two states that on 18th of August 2019, this column got delivered, right? So you've got these two columns. Column one has some missing values. So you look around that, hey, I cannot perform mean, I cannot go for median. These are categorical or date time in nature. So I should go for mode. You go for the most frequent value. Turns out the most frequent date is around, it could be any value. Let's say it's around 23rd September 2019. So you find that 23rd September 2019 is the most frequently used order date. Most of the orders were placed on this date. You use this value and fill it in everywhere there's a missing cell. A problem that might occur is the order date that you filled in will be 23rd September 2019, while the dispatch date or the shipment date, which is in real, shows that the order got shipped on 22nd August 2018 or 19. So you ordered the product on 23rd September and it got shipped on 22nd August. That's completely impossible. Until and unless someone was using a time portal, that does not happen in real life, right? So that's why you cannot go for most frequent or modes or any of these methods blindly. You should know your data. You should know what kind of problem you're dealing with, what kind of distribution you have. And you should think about what problems might occur if I go for any of these values or any of these methods. And to do that, you need to understand what are the pros and cons of this, of every possible method. I've already told you about mean, why is it used, why should not be used. I've told you about median. I've told you about mode, the pros and cons. Lastly, it's constant value. So the name is pretty clear. You can use any constant value. It could be anything. You're talking about gender again, male, female, you have got missing value. You decide you will replace them with NA. NA is not applicable, NA and whatever constant you want. You can go for that. Again, side effects or problems. These NA values that you're filling in, they do not convey much of the information, but they are still pretty better than going for a misinformation, or not giving anything is still better than giving something wrong, right? So you have to make this kind of a trade-off depending upon what problem you're solving. It also depends upon the type of missing values you have. So missing values are of three types, basically. Missing completely at random, missing at random, and missing not at random. So MCAR, MAR, and MNAR. Take this with a pinch of salt. I might be a little rusty on the names and let's call them definitions, but mostly these are the three types. And missing completely at random is when a value or a missing value has no reason of being missing. So it could be a human error, a system error, or anything, but it's a randomized value. I'm talking about what? I'm talking about the date of order. The date of order is missing. There is no reason or specific reason why anyone would not want to present the date of order, right? So if those values are missing, it's MCAR, missing completely at random. Then there is MNAR as well, the completely opposite, missing not at random. So I'm looking at a data set. It has two columns, age, and in fact, it has two columns, three columns in total, age, gender, and salary. You'll see that in age column, there are pretty much missing values, let's say 35, 40 missing values. In salary columns, there are again 25, 30 missing values. Genders are completely filled. Now, don't take my word on it, but it's a healthy example I'm taking. So you start diving into the data, you see that, okay, wherever the gender has been mentioned as female, you can see that 35% or 40% of the missing age values correspond to female, or let's say 75 to 80% of the missing age values correspond to female gender. Likewise, 75 to 80% of the rows where salary is missing have gender as male. So it is a common tendency or a common belief that males do not want to share their salary and females do not want to share their age. So just a healthy example again. So if you look at from this perspective, you'll realize that these values are not missing at random. They were omitted on purpose. So you might not want to do much with them because the author did not want to share these values. So they being missing, these values being missing actually convey some information. So on these, you have to think on these thoughts. You have to think about why and exactly the reason why particular value is missing. What does the missing value convey? And what are the pros and cons of the available methods that I can use to treat them? Based on these decisions, you can, or based on these thoughts, you can decide how to proceed with those missing values. And once you're done with it, your data will be a bit better than it was earlier when it had missing values. So more or less, that's the general idea about imputation. Let's see what exactly we've got. I think we've got a question. Is it still the first slide? I see only the first one. I'm not sure which slide you're seeing, but right now, I hope everyone can see the slide title imputation. If anything else, please let me know in the chat. Correct. Okay. So yeah, the slide right now is imputation and you're still discussing about it. I hope, I think it's some error on your end. Victoria, please see if you can correct that. Moving on to the next step, which is outliers. So as I was talking about outliers in the previous slide and even the slide before that, outliers can be understood as those values that do not confine or do not lay themselves to the normal distribution of your data. Again, the normal distribution I'm talking is not the statistical normal distribution. There are various distributions. We have normal, we have binomial, uniform, Bernoulli, we've got Poisson distribution, exponential and whatnot, but the normal distribution here does not mean those statistical ones. The normal means, let's say that you've got 1,000 rows of data and 950, 980 rows of data or 980 values out of them confine themselves to a specific range. Again, let's say the age example. So you have 1,000 age values or 1,000 different people, and 980 values out of them fall in the range of 18 to 55. It's a working class data. So 18 to 55 seems, or 18 to 56 or 58, whatever you want. Let's take it 18 to 58. 980 rows of your age values confine themselves to this range, 18 to 58. Then you've got 20 other age values, which are saying either negative, zero, or it could be, let's say 5 values are negative, 5 values are zero. Then out of the remaining 10, you've got all of the 10 values as between 10 to 15 or 10 to 18. Now, if you look at the data this way, you'll say that these values, these 20 values are outliers because they do not confine themselves to what the other majority part of data is telling. The majority of data says that, hey, the age should lie between 18 to 58. 98% of data says that, but these 2% of these values, they're saying that, hey, we are not going to lie in this range. We lie in some other range. So these are outliers. Now, what could be the possible reasons why these values occur? Let's look at these 3 different values that I was talking about to understand why they might have occurred. The first set would be the negative value or the zero values. So someone has entered their age as -10 or something. Someone entered as 0. So theoretically, it's not possible for anyone to be negative or zero age, right? That's not possible for anyone. So these values, if someone was not tricking or pranking with your system, these values have to be due to a human or system error. It's not real values. Either someone tricked your system, someone was having fun, or system crashed at some point. That's why these values are coming, and they do not make much sense to your data. Your model is better off not knowing that people could be zero or negative aged as well. You do not need that information, right? It's an error present. The other segment, or the last segment, that was people stating that their age is between 10 to 18. Now that's an outlier based on your data, but those values are real. So people could be 10 to 18 years of age. People are 10 years old, 11 years old, 18 years of old. Just because they do not confine themselves to majority of the data does not mean they are incorrect. They are outliers. They are outliers, no issues, no doubt about that, but they're not incorrect. They are real values. They just fall out of the range that other data lies themselves in. Does not mean you have to get rid of them. But we will talk about the treatment in the next point. So let's say that now you have, I hope you have got a brief understanding of what outliers are. If anyone can give me a yes or something in the chat, if you've got a brief understanding of what outliers are. Yes, thank you. So next step would be, how do you detect outliers? So now you know what outliers are, you're out looking for them. But how do you detect what outliers are? So outliers can be detected using various methods. We've got statistical tests like Z-score. We've got IQR or interquartile range. Then you've got the most easy, or the let's call them most appealing methods, the visual methods, box plot and scatter plot as well. So we'll start with the Z-score method. Z-score tells you that if you take out the Z-score value of any data, the equation, I'll share it after this. But if you find out the Z-scores or the standardized value for any cell, it should lie in the range of -3 to +3 for that particular value to not be an outlier. Now, the intuition behind this would go into the empirical formula for normal distribution. So just a brief hint on that. The empirical formula states that 99.8% of your data, assuming your distribution is normal, so 99.8% of your data should lie in ±3 standard deviation of your mean. So when we use that intuition, Z-score says that if whatever value you're looking at, if it lies between, if the value, the Z-score value for that row is less than equal to 3, or it lies in the range between -3 to +3, your value is okay. If it is less than -3 or greater than 3, it's an outlier. How do you calculate the Z-score? Z-score is pretty simple. All you'll do is you'll take your value. Let's say that your value is X. So the equation would be X minus mean of the data divided by the standard deviation. So the equation is Z equal to X minus mu by sigma. X is your current value, mu being the mean, and sigma being the standard deviation of the data that you're observing. So if the outcome of this particular equation is less than -3 or greater than +3, it's an outlier. Else, it's a, let's call them normal or good to go points. Do we have any questions? Session will be more interactive. Okay, let me do one thing. I'll get on the interactive part, I'll get on the visual part or the data part after this slide, or after we have gone through the topics. I'll give you a brief example of what exactly these values might look like. It will be helpful, agreed. But moving on the next point, the IQR or the interquartile range. So IQR is another formula, another equation that you can use to identify what values are outliers and what are not. IQR is the range of values that lie between first quantile and third quantile. So does anyone here know what quantile, 25th quantile, 50th quantile, what these values specify? Any yes or no in the chat? Okay, I'll tell you in brief. Yes, amazing. For the other people, I'll tell you in a brief idea. So let's say that you have got a data distribution, descriptive statistics, amazing, Chandrasekhar. So, okay. So if you've got a data distribution, you try to divide it into buckets. You want to see what are the 0 to 25th percentile value. So you want to check, hey, if I divide it into 4 equal buckets, 25, 50, 75, 100, I want to know what kind of values lie between 0 to 25 range. That is, what is the lowest 25% of my data? That's 25th quantile. Then we have 50 quantiles, 75th quantile, and so on and so forth. You can have any values you want. So IQR is the range of values lying between 25th and 75th quantile. That is the first and third quantile. You take the range between that, that's your IQR. The difference between that is IQR. But how do you use IQR to calculate or find whether a particular point is outlier or not? So the equation is written down. You take the Q1 value or the quantile 1 value, whatever you have in your data, the 25th quantile, 25th percentile value, sorry. So Q1 minus 1.5 times IQR. So you take Q1, or you take the 25th percentile value, you take the 75th percentile value, you subtract these two values, you've got the IQR. Now, Q1 minus 1.5 times IQR is the lower bound, and Q3 plus 1.5 times IQR is the upper bound. If any value in your data confines themselves to this range, the range between these two lower and upper bounds, it's okay to go for it. If it is less than the lower or greater than the upper bound, you can call them as outliers. Again, I am saying them, you can call them as outliers, but they're not definitely outliers. Outliers, they are hard to catch if you, and you'll need some domain expertise and data knowledge to catch them. But these equations, these methods can help you identify few of them. The next one is scatter plot. Now, scatter and box plot are two visualization methods. I'll talk about scatter plots because it's relatively easy to identify an outlier. So you've got your data, you've got x-axis and y-axis. It could be any two axes. Let's say that you've got x-axis is height, y-axis is weight. So you want to see what kind of distribution does height and weight follow. You plot all your data between these two axes, and you see that, hey, though majority of my data lies at a particular point, I can see 2, 3, 5 values that are extreme upwards or extreme lowerwards, right? You can say that, hey, on a general note, my height and weight are related on, let's say, 22 point something basis. So my weight is going to be 22 times my height in meters or something random. But there are 4 points which states that height is 5 feet, but the weight is pretty low or pretty high. We have different body types, right? So the values could vary. So if you see those points in the extreme corners that do not confine themselves to the majority of distribution, those are outliers for you. And it's pretty easy to spot them if you use this method as well. It's not statistical, it's more of a visual method. So it kind of helps people to identify these values. So let's say that you have done all these tests, whichever test suits you. It could be scatter plot, box plot, Z-score, IQ, or whatever suits you. You've done that. You found out what exactly are the outliers or which points are outliers. Now, what do you want to do with them? There's a common notion floating around that outliers need to be treated. You need to do something about them, else your model will not be optimal or something. But that's not completely true. Not every outlier is bad. As I mentioned earlier, outliers could be due to many reasons. It could be a system or human error. It could be real values as well. So let's take the age example again, right? Or let's take a different example. Let's say that you're working for any communication or telecom provider. You're working for Airtel, Jio, or something, and you've got the total number of minutes a particular person talks in a month, right? The talk time for the total number of minutes consumed on phone. You see that majority or 95, 98% of these values lie between 500 to 1000 minutes. That means 98% of your users, they consume 500 to 1000 minutes of their 1 month data. So they're talking to someone as they're talking on phone for 500 to 1000 minutes per month, right? 98% of them. Rest 1% is stating that the total minutes consumed is 10 lakhs, while the last 1% is stating that the total minutes consumed is 300 minutes or something. Now, I would like to ask the audience here if you can tell me, what do you think is more probable in occurrence? Is it possible to have people talking 10 lakh minutes on phone per month? Or is it more probable to have people talking 300 minutes a month on phone? Anyone, can you tell me in the chat? Let's say A is for 10 lakh being more probable or possible, and B is for 300 minutes being more possible in real life. A or B? A. Amazing. When, I mean, B is the, yeah, 300 minutes is more probable. I mean, I'm not degrading or demystifying anything. People can go for 10 lakh minutes. People are doing a lot of stuff these days. So 10 lakh is possible as well. But 300 minutes is actually more possible. And although, yeah, thank you. And although this 300 minutes does not confine to your data, does not mean it's wrong information or it's a misinformation. You need to do something about it. No, you don't need to do something about it. Today, 300 is actually falling outside your data distribution. It could be possible that tomorrow the distribution changes. People start talking less and something. And you need this 300-minute values. You need your model to know that, hey, these kind of values can come out. This is a possibility. You can observe these values as well. On the other hand, 10 lakh minutes, I would say possible, but not probable. It'll mostly be some error. It could be 10,000. In fact, 10,000 is even higher as well. So it could be 1,000, but 3 zeros got added by mistake or something. But you don't need that kind of value in your data. You don't want your model to learn that, hey, someone can talk 10 lakh minutes. even your model will start pointing out that something is wrong, right? 10 lakh minutes is not probable to do. So you don't want that kind of data which you know does not make much sense. But the one that does make sense, no matter what it states, it could be lesser or higher than the values. But if it is real data, if it is telling you some information, it is better to keep that. Now, what will you do about those 10 lakh rows, those rows that says 10 lakh minutes? You can drop them. If you've got a million rows of data and 100 of them says 10 lakh minutes, you can drop them, not an issue. But what if you cannot drop them? You can replace those values with IQR boundaries. So 10 lakh is again way over the upper boundary. Q3 plus 1.5 IQR would be very, very low than 10 lakh. So you can replace 10 lakh with Q3 plus 1.5 IQR value. And if it is less than the lower boundary, you can replace them with lower bound as well. You can use any other methods. You can go for mean, but I would recommend not to because it's sensitive to outliers. Your data will get corrupted up to a bit extent. You can go for median. You can replace those values using median as well. Just find out the median of your data, replace those outliers with that. And again, if the data is correct, if it's an outlier but still correct, it depicts real values, I'd recommend you keep them in your data. It will be helpful. What if 1,000 rows are there in that 500 are zero, other 500 ranges from 1 crore to 5 crore? What exactly are these values, 1 crore to 5 crore? I mean, what does 0 and 5 crore specify here? Can you help me? Mortgage. Okay. I mean, kudos that someone is paying 5 crores of mortgage. Amazing thing on that. But if it's saying zero, 50% rows are zero and 50% rows are 1 crore to 5 crore, it will again depend upon what kind of model you're building. I mean, if your model is focused on loan disbursements or the ROI you should charge, then I would say zero values are not giving you much information. If you're working for a bank and you want to check that, hey, are we giving the optimal ROI? Should we increase the interest? Should we decrease the interest? And you see that you've got 500 rows that says that these people are not paying any mortgage, they are rent free or anything. What kind of help will you get from that information to calculate the ROI? They're not going to be much useful for you, right? On the other hand, the one that are paying 1 crore to 5 crore mortgage, you can expect some information from them. You can see that, okay, what are the salary ranges? What is the age value? And some other features. And based on that, you can determine whether or not the ROI is optimal. So what to do with outliers will again depend upon the type of problem you're trying to solve. It's, I think, if I'm not wrong, it's a great saying. No fit. Okay, there is no silver bullet in simple terms. There is no silver bullet or free lunch. One specific thing will not help you solve every single problem on earth. If it was that easy, data science would be a piece of cake, but it's not. You need domain knowledge as well as data knowledge, right? It's data and science. You need both of them. So how you approach these problems, how you solve them will depend upon the type of problem, the kind of results you want, what you're trying to achieve. So I hope I was able to shed some light on your problem, Surya. Moving on to the next part. The next part is feature engineering. So feature engineering, I mean, is pretty clear in itself. It's two terms, feature and engineering. So for anyone who might not know, features are the columns in your data. So we call columns as features. What you mean by feature engineering is you can go crazy with your features. You can generate more number of features by combining them, by splitting them, whatever from your existing features. You can say that, hey, I've got way too many features. I do not want all of them. So you can go for feature selection. You can reduce your feature set size by saying, I want the top 10 best performing features out of these. Or we have a thing called cursor dimensionality. I won't discuss in depth about that, but in simple terms, cursor dimensionality means that you've got way too many features and way too less rows. So with a distribution of this type, when you have higher columns and not so high rows, your model is going to overfit. You need to reduce the columns. You can drop them, you can drop the non-top performing, but in a scenario where all of these columns, let's say you've got 100 features and 300 rows or 50 rows, 60 rows, somewhat close to that. You want to reduce your feature size, but 100, all of them are giving you information, are valuable to your model. So you cannot drop any of them. That's when you go for dimensionality reduction techniques. You've got PCA, you've got LDA and various other autoencoders as well. What these techniques will do is they'll try to combine your existing feature set into one. So in simple terms, you can assume that, let's say out of 100, it picks up 10 features. it will try to combine them into a single feature and give it to you. So now your feature set is reduced from 100 to 10 by 10:1 combining ratio. This is not these things work, but just an example. So this way you can keep the information. The variance drop will be pretty less. The information drop will be pretty less, but the feature set size will reduce drastically. The downside is you lose the explainability. So even if your model gives you amazing results, even if you're achieving whatever metric you dreamt of, you don't know what kind of feature is contributing how much. I'll get to that in a minute again. But how do you proceed with feature engineering? So let's start with generating more features, right? So let's say you've got a date column, order date again. You've got order date. What you can do is you can split it into multiple values. You can get a column stating date of month. You can get a column stating week of the year, or day, let's say day of the year, whichever day it is, 0 to 365. Then you've got some other two features. One feature could be about the price, another feature could be about the quantity order. You can derive a third column talking about the unit price. Take the price divided by the quantities, you'll get the unit price as well. So you can use this basic arithmetic transformations, or let's say splitting of features, to generate more features. Let's see, we've got some questions. How is the t-SNE model for dimensionality reduction? t-SNE is actually an amazing model, but honestly speaking, it is a bit out of the course for this discussion. I mean, t-SNE, when you're talking about t-SNE, you're going deep down the statistics. So we're getting some questions. Yeah, I see t-SNE is pretty famous or popular here. So it is an amazing model. I mean, talking about any model, it will do the job you want. It will give you the results you want, but it kind of depends on what extent you are going to. You can, if you want something fancy, you can go for autoencoders as well. Autoencoders are simply, you take a neural network, you feed in your data, you take out the output from hidden layer, it's already encoded, right? You have reduced the dimensionality. But it depends upon what kind of problem you're trying to solve again, and what extent are you willing to go to. So you have to make a trade-off. You have to balance between these things to choose what you should approach. Rest, I'd say everything gets the work done. It's just how you want to approach it. So getting back to feature generation, you can use many techniques. As I mentioned, you can go for arithmetic transformations, you can go for splitting, you can go for combining them to get more features. And you do this when you do not have enough features. So let's say you've got 10,000 rows and 3 features. So that's not a pretty good scenario. Or let's say that you have got 3 columns and 100 rows of data. So it's pretty simple for your model to get anything out of it, and it is more likely to underfit. You will not be able to capture the pattern or information you want out of that. So you might want to explicit, or you want to extrapolate or generate more features out of these three. That's when you can go for feature engineering. The second part is feature selection. So the most simple or the most commonly widely used example that I can think of is, you're working on grades prediction for students, right? You've got columns as the marks obtained in last year, the number of hours students spends on co-curricular activities, TV, whatever, the number of hours they spend studying. And based on these 3 columns, you're trying to predict the kind of GPA or CGPA they might get this year. Pretty amazing. You'll get the values, right? Now you're saying, hey, I'm also going to add gender column. I'm also going to add roll number of the student, the name of the student. I'm also going to add the address of the student, or the kind of atmosphere that was on the exam day, though it might be helpful, but not much. And you keep on adding random stuff in your columns, right? You fit your model, you train it, you go for the R-square test, the R-square score. R-square score has increased, and R-square score will always increase. If you keep on increasing your columns, it will either stay constant, but most likely it will increase. Does not mean the feature is useful. You check the adjusted R-score value, you see that, hey, initially with those 3 columns, the adjusted R-score value was 0.85. After I added these crap columns, these 4-5 useless columns, the R-score increased, but the adjusted R-score fell from 0.85 to 0.72. What does that mean? That means that although you increase the columns, you're not increasing the information. You're simply telling the model that, hey, this is some garbage, just learn it. It's not useful, right? You do not want your model to learn garbage. So you can either drop those columns, but how do you decide? Now, in this scenario, it's pretty easy to say that, hey, the gender, the name, roll number, address does not make sense. but it's not that simple always. Sometimes you'll have to be picky about which columns you want. And that's when you can use feature selection. That's another domain of feature engineering. You have various methods. So for regression, you've got F regression or something. Classification, you've got F classification. You've got specific functionalities in libraries. If I'm not wrong, in sklearn, the popular one, you've got feature selection as well. You can directly import that library and functionality and use this. What it will do is it will ask you that, hey, how many features do you want selected? Okay, I want 10% of the available features. I've got 100, I want just top 10, that is 10%. So now it will generate different subsets of your existing feature set and say that, hey, based on the score I'm calculating, the R score, R square score, adjusted R square score, whatever metric preferred, based on these scores, this particular subset of 10% features, let's call that subset C. So out of 100 features, you want subsets of 10, you can get the combination value, it will be pretty high. So it says that, hey, out of all those subsets available, subset C is giving the highest adjusted R square. This is your answer. You need that subset C. You go with that. You're happy with that, right? So this way you can reduce the number of features available and cherry pick the top N or top K of them. Last one, as I was mentioning, is curse of dimensionality. Same problem, pretty much same problem. You've got 100 features. You want to reduce it down to 10, but you cannot afford to drop any of them. All those 100 features are important for you. They are giving you some information you cannot afford to lose. So you cannot drop those columns. What you end up doing is you end up doing techniques like PCA, principal component analysis, LDA, linear discriminant analysis, autoencoder. TSNE was mentioned repeatedly, so that as well. What these models will do in general, do not take my word for it, because the exact definition, exact working will get pretty complicated, and I like to keep it simple for now, for this session. So what these methods will do is they'll take out all these different 600 columns that you have, combine them into different subsets. So it takes 100 columns, let's say it takes 10 columns, combine them into one, another 10, combine them into one. This way you get 10 columns that contains the information of 100. Now you might decide that, hey, I do not want the last 10 columns. They're not giving much information. You drop them. And as it occurs, you lost 5% of information. So you dropped 10 columns, you lost 5% of information. Now your model still contains 9 columns with 95% of the information available. Pretty good scenario. But what's the problem here? I mean, everything has a catch, right? So the catch is you train your model on this data, this reduced data, you get some answers. Now, someday a particular guy or girl comes to you, co-worker, client, investor, whatever, they ask you, hey, you're telling me that, let's say it's a sale-based data. You've got the amount of money you're pushing into different ad sources. It could be Google ads, Facebook ads, Amazon ads, whatever. You've got 100 different sources you're pushing money into, and a column that tells you about sales. So now what you do is you combine those 100 columns into 10 or 9, and you calculate the adjusted R score, whatever value, and the values comes out to be 0.95. You're pretty happy. Your team is happy. Your manager is happy. The client is happy. 0.95 score is pretty off the roof for them. 10 days later, they come to you and say, hey, although the model is good, can you help me out with what kind of sales I'm getting from Facebook ads? I'm pushing some money into Facebook. Just look at your model you have built and tell me what kind of ads I'm getting or how much contribution is coming from Facebook. You're stuck there because your model does not recognize Facebook, right? It got a combination of columns. So Facebook might have got clubbed with Google, YouTube, Amazon, Walmart, whatever ads, 10 columns got clubbed together. Facebook was one of them. And now your model does not know what Facebook is, what Facebook does. It can tell you that, hey, out of those 9 columns you fed me, column 1 is 35% responsible. Could be possible that Facebook lies in column 1, but how will you know? Even let's say miraculously, some miracle happened, your system starts speaking to you, the model you trained, it gained voice and it pointed out that, hey, column 1 contains Facebook. How are you going to know that out of all those 10 columns that have been combined into column 1, how much contribution is Facebook making? You do not know that, right? So that's the kind of issue with these techniques as well. And you have to check what kind of problem you are facing, what kind of solution you want, what are the trade-offs, and up to what extent are you going, or are you willing to go? Based on these things, you have to make these decisions about whatever we discuss about imputation, about feature engineering, about outliers, and there are pretty other stuff as well. We have got skewness, we have got kurtosis. I won't discuss about them right now. They might get a bit descriptive in nature, but for this session, let's keep it at these three things. So once you've dealt with all this, you look at the data and then you'll start thinking about, hey, based on everything I have right now in front of my screen or on my screen, I might think about using this model or this fancy ML model. For some problems, even machine learning is not even required, but assuming you want to use that, it is required. After cleaning your data, after processing it, after feature engineering, that's when you look at it and start thinking about what kind of model you want. If you go in the reverse cycle, if you look at the data and you're like, hey, I'm going to use random forest no matter what, the outcome will mostly not be what you're expecting, right? So you need to do these things, you need to think of these things. And I know I'm repeating it again and again, but trust me on this, you need domain knowledge as well as data knowledge before you do anything. So let's see, you've got, I think, 2 questions. Is there a thumbnail rows feature optimal for all promotion? No, there is no thumbnail for the ratio, as again mentioned. It all comes down to what problem you're solving and what kind of a data you have in hand, right? So for some data, let's say that the example I took about predicting the grades. So you might say that, hey, I've got 3 features: the number of hours student studies a day, number of hours they spend playing or watching TV or co-curricular activities, and third one being their average performance for past 5 years. Based on these 3 columns, you've got 100, 200 rows of data. You're good to go for prediction. Your data is not that complicated in nature. This is a pretty simple linear regression. If you plot it, you'll see a somewhat straight line between these 3 values or 4 values, and you're sorted for it. That's good. But what if you're trying to predict the sales value that I was talking about? So that's a different domain called marketing mix modeling, where you take into account the kind of sales each advertisement source might be deriving or might be driving. You want to know what kind of sales I'm getting from Facebook ad, what kind of sales I'm getting from Google ads. There you'll need all those columns that you're putting money into, and a decent, I'd say, in fact, more than decent number of rows, because that information is pretty complicated to capture. So there is no thumbnail or rule of thumb for this ratio. It again depends upon what you are doing, what your objective is, and what you want to achieve out of it. So these, you have to keep in mind these things before making any decision. And I'll repeat it once more on the cost of being repetitive. Do not start thinking about pulling in ML model as soon as you start hear the term data science. As soon as someone comes to you stating, hey, I'm solving a data science problem, do not directly jump into machine learning. Think about data first. Look at the data, see what kind of problems it has, what story the data is trying to tell. And once you identify the shortcomings, the pitfalls, think about how you can solve them if they need solving. As I mentioned in the imputation case, when the missing age values confined to female gender more and the missing salary values confined to male gender more, that kind of data does not need much tampering, right? That those missing values in itself are information. On the other hand, talking about outliers, as everyone said, those 10 lakh minutes consumed a month is a pretty huge value. So you might need to do something about that. So identify the pitfalls and see if at all they need correction, and if they do, what kind of correction or corrective measures can you take. Once you are through with that, then start thinking, do you even need a machine learning model? And if you do, if the answer is yes, then it's the time to start thinking about, hey, what kind of model do I need? What story does my data tell? What distribution it follows? Make that choice based upon your data and not simply based upon what model you like or what is the most fancy model going around. Hey, I read XGBoost is the model that wins Kaggle competition, I'm going to use XGBoost. That's not going to work, right? You need to make those decisions carefully after you're done with the data. Now, I'll try to show you some examples. I mean, I do not have anything stored right now, but I'll try to pull something out. I guess we are pretty much out of time, so I won't be able to do much, but let me give you something. So let's say, again, I'll simply tell you what exactly we already discussed. Let's say you've got age column. You've got values ranging from what, 35, 18, 19, something going on. Let's make it easy for everyone. You've got these values, right? Till 39. Let's say this is your data. Now it repeats itself a huge number of times. This is your total data that you have, right? You'll see that, okay, if you can see the statistics, you'll see the mean value is 28.5, right? Let's say I remove this row. This 20 is gone. Yeah, Sai P, I see you've raised hand. Screen is not visible. Okay, let me share my screen again. Let me know once the Excel is visible. So I'm simply plotting something we've already discussed. We've got an age column, right? And we've got pretty amazing values. The distribution is from 18 to 39, and then it kind of repeats itself. Just for sake of this example. Uh, yes, thank you. So you'll see that the average value for this data, yeah. So the average value for this data turns around 28.67. Now a person is going to filter or enter that they are 28.6 years old. It'll be 29 years old, right? So you look at this, you'll say that, hey, let's go for the mean value imputation. Let's go for 29. What if we have some other values, 1,000, and then a pretty amazing human, the immortal kind. So now let's look at the mean. The mean or the average comes around 1,528 years. So either all of your participants are borderline immortal, or you've got outliers in your data. You cannot fill in the missing value of 1,500. People won't like it. Model won't like it. The investor won't like your clients being 1,500 years old, right? This is a kind of scenario where mean would fail. You can go for median in this, and once you figure out the median value, you can start using that to impute it. Now let's look at a different example. Let's look at height and weight, the one we discussed. The height is somewhat constant. Let's make it like this, although a person to be 7 and 8 feet is probably problematic. Yeah, and this person is around again 5 feet tall. The weight in kgs, let's say, ranges from 70, 71. I'll look at the questions in a second. It ranges around this range. Can we use ML for small data set? I would say don't use ML for small data set. Your model will overfit. If you have 30 rows of data, you do not give your model enough information to learn something, right? And you do not want that. Your model will be overfitting or under, depending upon what kind of columns you have. Your model will either underfit or overfit, but in any scenario, 30 rows is not recommended. Yeah, these are pretty straight lines right now, so you won't be able to get out much out of it. But let's say that you've got your height on the x-axis and your weight on the y-axis. You'll see that most of your data lies around this particular circle, which means it's okay. It's okay. But then we've got this guy who is 180 kg and another person who is 22 kg, 5 feet, 22 kg. Now you can see that although most of your data confines itself into this particular region, we've got one value lying way above and another value lying way below. These two are outliers. You can look at the data, you can look at the distribution and identify, hey, these two are outliers. I might need to do something about them. Although you shouldn't do, because people could be 180 kgs and people could be 22 kgs. So depending on what kind of outliers they are, what value do they, what information do they deliver, you will have to think about what to do. But you can use this simple scenario to see if there is an outlier by using scatter plot. You can do the same by using box plot, z-score and IQR as well, but this is pretty simple to do. I'm not saying use scatterplot always. Go for statistical tests as well. They are much informative in some sense, but yeah. Let's see. I think that's all from my side. If anyone has any questions, I'll be up for them now. So okay, we've got Q&A. What kind of machine learning or deep learning we can make to put in our resume? By the way, currently I'm in third year. Hi Vivek. You're in third year. I would say I think I pretty much answer something on the lines of this question. It needs to resonate with the kind of problem you're trying to solve, the career choice you're trying to make, or what interests you more, right? Machine learning and deep learning, they are very fancy term, but they are being thrown around way too loosely around the industry. You'll see people are putting the Titanic data set or the Iris data set in their resume, or even stock prediction. Take it from me, do not use these three scenarios. Uh, Titanic and Iris are way too common. Everyone is putting them in resume. They do not deliver any information. And stock market is way too volatile to be predicted by ML model directly. So it's more of a negative sign than a positive sign by putting these three models. But if you are more interested in machine learning, let's say you understand the mathematics better, again, before even thinking about the project, start looking into what these models talk about, what exactly does linear regression talk about, not just simply importing the sklearn file or library, what goes behind these things. And then once you have figured out that, hey, the mathematics, the equation, the derivation of these classic machine learning models resonates more with me, I'm pretty much comfortable talking about random forest than I'm about RNNs or LSTM. Might be you should think about going for a classic machine learning modeling project. It could be any project that you find interesting. It could be trying to predict the air quality index. It could be trying to predict the number of cars you can see on your road any day. Any kind of data that you can get your hands on, which conveys somewhat real information, is more than likely helpful for you. But again, do not go for these three: Titanic, Iris, and stock prediction on your resume. You can go for the two above, Titanic and Iris, for your practice for getting your hands dirty, but don't put them on your resume, these three. If data is highly imbalanced and there is a mixed behavior in both class, how can we tackle this situation? Amazing question, Priyanshu. So you've got a lot of techniques to handle data imbalance or class imbalance. One is the top of my mind is overfitting and oversampling and undersampling. In oversampling, what you'll do is you'll take the segments of your majority or the minority class, and you'll try to duplicate them. So you'll take the existing data in your minority, and you'll try to create some more samples along the same lines. So it could be linear transformation or something. This way, you're increasing the number of rows in minority class. Undersampling is you'll try to reduce or just get rid of some rows from your majority class. With a pinch of salt, both these methods have their pros and cons, so choose wisely. Undersampling would mean you are getting rid of some rows, so you're losing some data. Oversampling can lead to overfitting because you are simply regenerating existing data. Another thing you can do is you can play with the metrics. You have different metrics. You've got precision, recall, balanced accuracy, and whatnot to help you identify the performance of a model irrespective of the majority minority class. So that's something along the lines you can do. I'm working in thermal power plant, 13 years of experience. We are developing process optimization model, which optimizer best suited for process parameter. Okay, first of all, it's pretty open-ended and I would say vague problem because I'm not able to understand what exactly are you trying to optimize. But assuming that you want to optimize something along the lines of categorical value, you want to optimize the number of hours particular machine is running or something, I would say go for a regressive. Obviously, regressive value, it could be adjusted R square or something. Regression problem, again, it's pretty open-ended, as I said. It could be that you want to reduce the number of hours and you are looking at the R square value, the adjusted R square value, the MAE, mean absolute error, mean squared error. It will depend upon what kind of trade-off are you ready to maintain. What does your data say? If your data has outliers, MAC, let's say that on a specific day you ran your machines for 20 hours and on average you are running them for 12 hours. So you want your model to punish the day it ran for 20 hours. That is, you want your model to heavily punish those outliers, those extreme values. Go for MAC, mean square regression. Screen is not, I haven't shared the screen. So that's why it's not visible. If you do not want to go for punishing those heavy extreme outliers, go for MAE, go for adjusted R square. It depends on the problem. How can ML deal with collinearity? Should it be tested before? So multicollinearity is exactly an issue that kind of troubles linear regression. It should not be there. Other models like random forest, bagging boosting model, they're not much affected by multicollinearity. But if you have multicollinearity present and you're thinking about using linear regression, I would suggest going for some tests like VIF, variance inflation factor. Run this test on your data, it'll tell you some kind of values. Then based on the values you get from this test, you'll identify that, hey, which two columns are closely related or which columns can be derived from other columns. You can either drop those columns if they are pretty explanatory or pretty derivative. You can go for PCA on this dimensionality reduction on this. That way you can deal with them. But collinearity is an issue with specific models, linear regression to be more precise. Other models like XGBoost and random forest not much affected by that. Got any resource for finding feature importance? Shapley, any idea where I can get resources? Shapley is actually an amazing feature tool, I would say. but Shapley will not tell you the feature importance exactly. Shapley, so there is a confusion around Shapley that I have noticed. Shapley is not telling you what kind of importance a feature conveys. Shapley is telling that, hey, if I'm taking the average prediction of my data set and I'm taking the prediction that my model got for, so let's say I have 1,000 rows of data, the average prediction is 500 and row number one predicted 300. So there's a difference between of 200 between the current prediction and the average prediction. Your Shapley will tell you how much your current feature contributed in getting that difference of 200. It will help you out if you're working with marketing mix modeling. You want to get those contribution for ads and revenue, but there are other simple things as well. If you want feature importance, you can go for random forest feature importance. So models have their own feature importances. You can go for random forest. You can go for XGBoost. If you're working with linear regression, the coefficient of any column is its feature importance. All those who haven't answered the feedback, okay, that's not so. Machine learning or deep learning projects, I think I've answered that, Vivek. Is this possible? You illustrate what you're talking about. I hope I've conveyed something. Any example where you can use IQ or outlier capping in practical situation? So again, as I said in the discussion, 10 lakh minutes per month is pretty improbable. Might be a good place for you to start looking into for IQR or any other replacement. How can we interpret the PCAs? The PCA, or the principal component axis, tells you what kind of variance has been captured by the single principal component. So PCA is a bunch of principal component axes clubbed together. The goal is to minimize the number of columns while maximizing the variance captured. The value or the importance of the individual PC is the amount of variance they have captured. And there are pretty much different tests. I'm not sure I remember the correct name, something with screen test or something that can tell you the amount of variance you have captured. But how to interpret two PCS or how do you calculate them, it depends. There are various formulas. So the most basic two I can think of is, you'll get the projection of your incoming data on a principal component axis. You can either try to reduce the distance between the projection or maximize the distance of the projection from your origin. These are the two ways, the most simple ways in which you get the PCs. Then, yeah, I think I've answered pretty much any and every question. If there is any other question, I'd say please shoot it out on my LinkedIn. We are already out of time. But if anyone has any other question, shoot it out on LinkedIn. I'll be more than happy to answer. Thank you. Thank you everyone for joining in. Should I last one? Okay, let's catch it on LinkedIn. Thank you everyone.